All right, this is part 3 of the Math 136 online practice test for the final. So I'm looking at problems 15 through 21 in this video, starting with number 15, which says match the graph to one of the following functions. And this is an exponential graph, which the typical, like say, since they're using base 7, typical y equals 7 to the x will have the following characteristics. All exponential graphs that are going to have a positive base typically would have this type of growth, which is called exponential growth, where they cross at the point 0, 1, and they have this horizontal asymptote at y equals 0. So this is what a traditional exponential function where the base is greater than 1 looks like, okay? So notice that the first thing I always take note of in these problems to help me narrow down what the picture looks like is that I can mark out the original one if it doesn't look like this. Second, if you see that your horizontal asymptote is at y equals 0, that means there's no vertical shifting, which means they shouldn't have a constant added or subtracted after or before your 7 to the x. So that marks out this because that has a shift down 1. That marks out this one because that actually has a positive 1 as a vertical shift. So now we're down to just these choices. The next thing I look at is if this point is included, and it is, so that means they didn't do any horizontal shifting. So that means you can't have any adding or subtracting inside your exponent. So that means those two guys are out. And then lastly, just what's going on here. This is a reflection where it's been flipped across the y-axis. When you have a y-axis reflection, that means you have a negative inside your function. Well, inside the function means that it would be in the exponent since that's where the x is happening. If you had a flip upside down, it would be in front of the 7. It would be like a negative times your 7 to the x. So this is the only case where it has the correct reflection because we do not have both reflections. Sorry, you're supposed to write your letter down here. So B is the correct choice. Okay, let's talk about number 16. This is a kind of what I call a complex exponential equation to solve. It's kind of going to bank on the fact that you understand how exponent laws work. I'm going to rewrite this problem in what we call substitution format in just a second, but to do that I have to prove that there's something similar in both of the first terms. And I kind of see 2's with x's, but it's not quite right yet. So I'm just going to remind you of two properties. If you have x to the second times times the third, you multiply those exponents and get 6. This has been multiplied together. That means we can break this back up. So this would be 2. I'm going to leave the x inside and then squared on the outside. An x and a 2 both on the same base would get multiplied together and would become 2x. So we're kind of thinking how this is being written. If you have x to the 2 times x to the 3, like this, you add the exponents, which is 5. These exponents have been added, so I'm going to split that into two separate problems. I'm going to call it 2 to the x times 2 to the first, because that's what it would have looked like before they added the exponents. And then minus 35 equals 0. So this is 2 to the x squared. This 2 to the first is just 2, so plus 2 times 2 to the x minus 35 equals 0. Anytime you have a matching base and everything kind of looks like it's quadratic because this is squared and this is to the first power, you can use something called U substitution to solve your problem. So we're going to call the 2 to the x as the letter U, and the only reason we do that is just to make this easier to factor. So everywhere there's a 2 to the x, we're going to call it a U. We factor this using normal factoring rules, U plus 7, U minus 5, U equals negative 7, U equals 5. But we have to remember that U was not what we were originally solving for. We were solving for 2 to the x. So 2 to the x equals negative 7, or the other option is 2 to the x equals 5. Now, if you raise 2 to any power, it's never going to become negative. So that's not going to make sense because when you raise 2 to the negative power, it doesn't make it negative. It just flips the fraction upside down. So the only one we can solve is this one, and we're going to solve it by taking a log of both sides. So log of 2 to the x equals log of 5. Bring the exponent to the front as a coefficient using our log properties. And then you should be able to just divide this over. So log 5 divided by log 2. So that's your exact answer. So log 5 divided by log 2. Now, the approximate means you have to type that in on your calculator. So let me get my calculator up. Here we go. So this is 5 log divided by 2 log. You may have to put your log button in first, just depends on the calculator. Hit enter. That is about 2.32. Are we rounding to the nearest, how many nearest decimals? 3 decimal places. So we need to write 2.322 because the 9 would bump that up. And that is it for that one. So even though it looks really nasty at the beginning, if you know enough about exponents to rewrite it, it becomes an easy to factor problem where you just had to do a back substitute and use logs. Okay, so number 17 says graph the function f of x equals x plus 2 squared minus 6 by starting with the graph of y equals x squared and transform it using shifts, stretches, compressions, or reflections. The first thing you need to know is what does this guy look like? So if you don't know, which hopefully we do since parabolas are one of the most common things we graph, you can make a little xy chart. So -2, -1, 0, 1, 2. If we square each of those things, that's 4, 1, 0, 1, 4. So we know if we graph that, that's 0, 0, 1, 1, 2, 4. We've got -1, 1, and -2, positive 4. So you get this U-shaped graph. Now, this is a transformation of that. When you have a plus or minus inside, it actually moves you left or right, and if it's a plus, it does the opposite. You have to think what would make this zero out. It would be a -2. So we need to move left 2. If you have a plus or minus after the squared part, that means you're doing some vertical shifting, and that's exactly what you see. So it's down 6. So you literally just need to use the tool for graphing a parabola, and usually that has you graph the vertex and one other point. And you need to figure out where these would move. So 0, 0 is going to go left 2, down 6. And I usually plot 2 of these when I'm doing it by hand. 1, 1 is going to go left 2, down 6. So hang on, so left, we're here. So left 1, 2, down 1, 2, 3, 4, 5, 6. We've got another guy that matches that. That's where -1, oops, hit the wrong button. Yes, I don't want that. That one's going to be moved there. And then if you want, you can move 2, 4 as well. So over 1, 2, down 1, 2, 3, 4, 5, 6, which means there's going to be a match over here as well. But you guys will be using the tool that allows you to graph parabolas to do that. Okay, number 18 is another one of these where you're trying to match the graph. So you need to know what does log base 4 look like essentially with nothing happening inside, just a regular x. So anytime you're graphing a log function and it hasn't been shifted at all, it's going to have a vertical asymptote of x equals 0. That's just by it being the inverse of an exponential. It'll have the point 1, 0 on it, and then the graph will look like this. It looks like an exponential that's kind of been flipped over and turned on its side. So the first thing I always ask is the vertical asymptote the same? If it's not, you're going to have plus or minus something inside with your x, because that would be a horizontal shift if this vertical asymptote is somewhere else. So since it's where it's supposed to be, I won't have any horizontal shifting. So no plus or minuses inside my log. I then look and see if the 1, 0 is also here, which it is. So that means I'm not doing any vertical shifting. I'm not moving this graph up or down. So it's not going to be any adding or subtracting before or after my log. Then we're looking at a reflection again here. So this is being reflected upside down. So once you reflect over the x-axis, then you know that you have a negative in front of your function. So it has to not be this because that's a negative inside. This is not the original. This has both transformations, which would make it flip over here if we had both. So it has to be G. Okay, and then number 19 says graph the polynomial function and then choose the correct graph, and they're counting by -5 to 5 on the x-axis, and they're counting from -120 to 180 on the y-axis, where each tick mark is about 20 units. They tell you that for reference, but to graph one of these, typically how we do it is we do 2 things. We look at the end behavior, which has to do with the degree of this guy, which he's already in standard form, so the degree is just the highest power, which is an even. And then we look at the leading coefficient. The leading coefficient is either positive or negative. This one is positive. If you have an even degree, your end behaviors head in the same direction, like both up or both down. And that means as we head towards the infinities, are we going to the positive y's or to the negative y's forever? So if you're even, they're going to head in the same direction. If you had an odd degree, they would head in opposite directions, like x cubed. One goes down and the other goes up. And then positive means they're both going up since this is even. So that means that it cannot be B and it cannot be C because those guys have end behaviors that are both going down. So just knowing that alone, you're down to two choices. And then the next thing is, can we figure out what those x-intercepts are or the y-intercepts, which I'm thinking this guy's not it because this does not look like it's going to have an x-intercept of 0. So we're going to try to factor this. So x squared plus an x squared minus, because it looks like we're going to have different signs since it multiplies to negative 100. And that would be, I believe, a positive 25 and a negative 4. Now this is imaginary. You can't solve that guy because it's got a plus 25, but this one is x plus 2 and x minus 2. So whichever one crosses the x-axis at negative 2 and 2, which it looks like at this guy because they're counting from negative 5 to 5 on the x-axis, that is the correct graph. Okay, number 20 is let's put these logs back together as a single log. So the first step is to put the powers back up. So this would be log base 6 of u to the 4th plus log base 6 of v to the 8th. If the log bases match and they're separated by a plus, you convert it back to a single log where you multiply the arguments. So that is what you would type in that blank. And then the last one for this part of the video is number 21. This looks like an exponential equation. The question is if you need to use logarithms or not, and that's based on if your bases can be matched to each other. Like if you can write both of them as like 2 to some power, then they match, or 4 to some power. But if you can't do that, then you would need to take a log of both sides and pull the powers to the front and try to distribute and solve. But this one, 128 is 2 to the 7th. So that would have an x on the outside still. And 4 is 2 squared, and that would still have negative x plus 27 on the outside. And then we just multiply the powers, essentially. So this would be 2 to the negative 2x plus 54 equals 2 to the 7x. And since the bases match, we set the powers equal. Add the 2 over. That would be 9x, divide by 9, and this is 6. So x is equal to 6. All right, that's the end of this video. The last video will be coming very shortly.